reduce CO2 emissions, power plants layer on complex processes, resulting in increased electricity costs. Net Power breaks this paradigm using a clean sheet approach to design an efficient, inherently emissions-free power cycle. Net Power uses supercritical CO2 instead of steam to produce power. Natural gas is combusted with hot, recuperated CO2 and oxygen, preventing NOx production. Burning with oxygen, known as oxycombustion, is typically uneconomic because oxygen is expensive to produce. Net Power overcomes this problem by recuperating the majority of the produced CO2 into the combustor, dramatically lowering oxygen requirements. The resulting working fluid of high-pressure CO2 and water is expanded through a turbine and then cooled in a heat exchanger. Water is removed, and the remaining nearly pure carbon dioxide stream is compressed and pumped back to high pressure. Excess pipeline-ready CO2 is exported before the working fluid is reheated in the heat exchanger and returned to the combustor. This breakthrough process produces low-cost electricity, eliminates water consumption, and is emissions-free. Power, truly clean, cheaper.
Well, once you strip off the sales pitch in it, it's kind of interesting. The so-called alum cycle. The time I showed this in 2021 was recording. They planned a plant in Texas to be able to show exactly what it was able to do. And this is an article in Science which talks about this, gives a nice schematic of it. The idea that you use natural gas, so it's not fossil fuel free, but you burn natural gas with pure oxygen, which you typically have to take out of the air, 10% oxygen, 90% nitrogen, by freezing it, cryogenics. You combust them together so you get a stream of gases, and you pass those gases through a turbine. Because it's pure oxygen and methane, and you're burning the hydrogen that's in the methane, it comes out as a pure stream of CO2 and water. Water you use to be able to use in arid regions or whatever, has obviously a lot of uses. And the CO2 you either can recirculate to recombust again, or you can dispose of it as pure CO2, which is what you want to do if you're disposing of CO2 to sequester it. So you don't, if you take it just out of the stack, it comes out of the stack at 90% nitrogen and 10% CO2, and that's a very inefficient way of disposing of a quantity that is expensive to pump underground in large volumes. So you want to reduce the volume and maximize the concentration. And so the alum cycle is one way to do that. It's kind of relevant today because we'll talk about this idea that, one, we have to prospect to get heat out of the ground, but also once we've got it, we have to go through a phase change to be able to pull energy out of it. And we'll talk about the thermodynamics of that to be able to talk about that process. So that's where this is relevant, I guess, for today. So I'll get rid of that. And I guess the other one, to give us a reason to live, so we're not just looking at equations all the time. See if this comes out okay. So geothermal plants, you probably recognize where this is. This is New Zealand, tucked away at the bottom of the world. South Island, North Island. There's a San Andreas-like plate boundary that goes up through the island. It's called the Alpine Fault, strike-slip fault, which is moving laterally but not up or down or over each other. And then it goes across the Cook Strait, and then the plate boundary is a subducting slab which goes underneath the North Island of New Zealand. So interesting case in point. We used to take students there. That's why these pictures we'll look at. There's a bit of kind of political friction between the South and the North Islands. The South Island is the one that has the mountains, no volcanoes, a fault, lots of hydropower, ski resorts in Queenstown, but no, and actually some fossil resources, has some coal up here. And the North Island is the one with all the population that uses all the electricity that comes from the hydro in the South Island. It comes across the Cook Strait in a DC link, direct current link, and is used there. And this plate boundary that is here that has a descending plate that goes underneath the island. You remember that as the fluids on that plate come out of the slab and go up into the mantle and into the crust, they develop volcanoes. So those volcanoes are exactly here. Taupo, Lake Taupo is here, is perhaps the center of them. Don't want to see that. And let's see who we have here. And so so this zone here, so you can imagine a fault here and a fault here. It's a block that's shifted apart, and it's the Taupo volcanic rift zone where many of these geothermal reservoirs are. I'm not sure what we have here. We don't see my lovely young lady friend. What do we have? So it's probably as good as anything. So this is Wairaki, which sits next to Taupo. We mentioned before, very first geothermal field that was exploited is Lardrello in Italy, which was a liquid-dominated field. This is Wairaki, which is the second one, maybe post-war. It's post-Second World War, 1950s, which is a steam-dominated reservoir. These represent individual drill pads. These represent the pipes that are taking the hot fluids with expansion joints, so they can contract or expand. The pipes themselves sit on rollers, so they can expand and contract as the temperatures change, and taking the hot fluids to be used in different locations. This happens to be an overlook for one of those. I guess I didn't want to do that. I just want to stay there. And what else do we have? And then they would take that material, they would off-gas some of it, they'd take the majority of it to turbines and flash the liquid to steam. As it changes phase, it drives the turbine blades and generates electricity from it. How do I get back to? That's how I get back. And once it's flashed out of the other side, then it would go through a condenser. And a condenser, I thought I saw one earlier. There. So this is just the geothermal fluids going through a region with fans pulling air through it, just like a radiator on a car. And so that is able to take the heat out of the steam, bring it back down from a vapor to a liquid, and then to re-inject it somewhere else in the geothermal field, so it maintains the pressure within the field that can be ultimately used. So that's kind of the job that we have ahead for us, is to understand the whole process. Alum cycle's not so relevant to us, but we can look at those individual components. Oh, I guess it is in that. In this. So I think this is where I want to be. So this. So we'll talk a little bit about the thermodynamics of these systems. We've talked a bit about it already, but this will just kind of anchor the things. So we'll talk about the characteristics of heat transport by conduction, convection, and radiation today, and we'll talk about phase changes in these systems and controls on that. So as a primer, I guess, we already know many of these things. If I work in one color, we know that the heat per unit mass is given by the temperature change that something goes through. If you heat it up by 100 degrees centigrade and it has a specific heat capacity of whatever it is, we know this heat capacity of water is 4,000 joules per kilogram per degree centigrade. So if we multiply that by the heat change, we get the amount of thermal energy in joules per kilogram, because we haven't included density in this particular part. So this is per kilogram. We know in SI units it's degrees centigrade or Kelvin. We know that 1 calorie is equal to 4.2 joules. There's this commonality between them. And 1 calorie is the amount of heat energy we need to raise the temperature of water by a gram of water by 1 degree centigrade. This is what I guess we'd call sensible heat change, in that there is no change in phase that occurs with it. It's only just changing the temperature, but everything else within the material stays the same. If the water were to flash to steam, then we have to worry about latent heat. And so that means as you go from, for geothermal fluids, from 99.999 degrees centigrade to 100.0001 degrees centigrade, that you essentially make no change in temperature, but you potentially pull heat out of the system through latent heat. And latent heat is what you have to apply to freeze ice in your freezer from water, or it's what you have to apply to the water boiling on your stove to turn it from liquid to vapor. So the latent heat of fusion is to change ice to water, to melt it, and the latent heat of evaporation is to turn water to a gas. And so what we could do is we look at the relative heat changes that are involved in so-called sensible heat changes, which are the first, no phase change, and the heat inputs that cause phase changes, and make comparisons between them. And so it's kind of wrapped up in the coefficients which control this. So sensible heat change is controlled by latent heat. Non-sensible heat change is controlled by latent heats. And the magnitudes of those coefficients that control that process, at least all of these are for water. We know this from last time, 4,000 joules per 4,000 joules per kilogram per degree centigrade, 4.2 kilojoules, just mixing up parameters. Latent heat of fusion and to melt ice is 334 kilojoules per kilogram, and 220/60 to evaporate water or to boil water and have it off gas as a vapor. So what we could do is we can compare those heat inputs that we need to do that to be able to raise a liter of water, kilogram of water, by putting in heat to it. If we want to evaporate it, the amount of heat input we have to put in to evaporate a liter of water, a kilogram of water, just by equating these two values, turns out to be about 80 degrees centigrade. So it's quite large. And of course, that 80 degrees centigrade at 99.99 to 100.00 is no temperature change, but it requires a large amount of heat input to be able to do that. Likewise, if we want to evaporate compared to melting, then the amount of heat that we have to apply for a kilogram is 7 times larger to be able to evaluate it. So we can play those games based on our knowledge of sensible heat transfer and changes in non-sensible heat transfer, which is due to latent heat. If we're looking at heat transfer, we have 3 modes. We've talked about them briefly before, at least 2 of them: conduction, convection, and radiation. Radiation's not so useful to us, but we'll perhaps chat about it briefly. Conduction is via Fourier's law. We've called this coefficient of heat conduction, and we've used lambda in our previous work. This is from a previous class that I used. So Fourier's law, but perhaps I'll revert to using lowercase k in this particular case. It's driven to give a flux as a function of gradient in temperature. The flow is in the opposite direction of the increase in temperature, so hence the negative sign here. Control that. The total heat flow, I guess if we've called this before Q. This is heat flux per unit area, which is thermal conductivity multiplied by the thermal gradient. And we talked about typical magnitudes. I think water was 0.5, we said last time, watts per meter per degree Kelvin. Rock was 1 to 6 or 1 to 5, I think we talked about. And it's large for conductive components, steel, you could imagine, and it's small for insulators, thermal insulators. If we want to look at the heat transport equation in terms of unsteady flow, transient behavior, in other words, if we look at this system here, take a snapshot of the temperature distribution in this bar now and 10 days from now, it will always look like this, between upstream and downstream and linear. If we change one of the boundary conditions, maybe make this temperature one lower, then the temperature will try and readjust to that magnitude. It won't go straight away to steady state, but instead you'd expect it to go at T1 and T2, and then T infinity would be this. So it would readjust to change its configuration. If we want to be able to solve that, we have to solve a conservation equation. This we talked last time about the fact that this first order derivative says heat energy in equals heat energy out in the x direction and typically in the other two directions as well, y and z. If we substitute Fourier's law in for this heat flux, then we get a second order PDE. It's referred to as a diffusion equation. It's a diffusion equation because it allows heat, temperature to diffuse through it. It's also exactly the same equation that can represent chemical conduction by chemical transport by Brownian motion, by diffusion, just by changing these coefficients and using concentration as the dependent variable, or by pressure diffusion in fluid flow by using pressure as the dependent variable and looking at the diffusion of a pressure pulse, not the diffusion of water, but the diffusion of a pressure pulse through the system. So the other thing you can do with this is that we won't solve it specifically in what we do, but we could look at the dimensionality of this and what the minimum number of parameters we can use if we want to solve it. So if in this particular case we start off with a reference temperature, which we could define maybe as a temperature that doesn't change, then if that temperature is T0, you could divide both sides of this by T0, which is done before, and then rationalize exactly what the parameters are that control it. Density, specific heat capacity, thermal conductivity, if you want to use lambda or K, either way. And if you pull out the derivatives, keep this x squared here because it's not an operator that's operating. D squared derivative just drops out, we don't care about that. And if we rearrange this by dividing through by rho c, so this goes away, we end up with a term where the relative change in temperature, and if we multiply both sides by temperature, which we can do, so this goes away as well. This is gone. We end up with only two properties. The two properties would be T over T0, this term here, a relative change in temperatures, which also exists here, and this term here. So this before was what we would refer to, this whole term was thermal diffusivity. It's also hydraulic diffusivity, which I'm not sure we need to talk about in this class. And so importantly, if we call this thermal diffusivity, we talked about it last time, this is one non-dimensional term. You can use the units that we have for thermal conductivity, watts per meter per Kelvin, time and length squared, meter squared. You'll find that it's equal to meters squared per second. We said that actually quite a good value for thermal diffusivity was 30 meters squared a year. And the relevance of that is that we can solve this differential equation, for instance, to be able to solve for temperature changes that occur, say, by conduction within a reservoir. And so, in other words, if you have a reservoir, which you could think of as a steel rod, which is conducting, and that you start off with this steel rod at some temperature that is T0. Actually, let's do it the other way because it's easier to think about. T0 equals 0. And then you heat this boundary here to T, which is this. Then you'd find out that the temperature change at time 0 would look like this, lowercase t0. It wouldn't be a straight line, but it'd be T1, T2, and ultimately T infinity, right? In the same way as if you imagine you change this boundary condition here, ultimately it'll become steady state because it's just flowing through a constant section. Then the change in temperatures you'd get would be this. And so if you think about it, the time it takes to get to this point here, which might be 50% of this change, you can actually define in terms of these non-dimensional times. So this would be a location. Each of these times could equally well be defined as a time multiplied by thermal diffusivity and divided by a length squared, this term here. And so it turns out that to get to this so-called non-dimensional time, each of these would be a characteristic magnitude. And the one that it takes to get to 50% of the temperature would be roughly equal to TD equals to about 1. Not exactly. A useful number to remember. And so physically what that means is if you were looking at measuring the temperature at this point here, to define what the temperature is, and you plot that temperature change as a function of this non-dimensional time, TD equals kappa T over x squared. So you know how long this is. This is x. So you know x, you know what the thermal diffusivity is, and you know what your time is as it advances. You'd find that this behavior would be that this curve would look something like this. This would be T minus T0 over T0. So this magnitude would be 1, just this magnitude here. And this would occur at a magnitude of TD approximately equal to 1. So in other words, you don't have to solve a differential equation. The standard solution for this comes out to be if you define this behavior in the minimum number of grouped parameters that describe this PDE and this physical system, it's 2 parameters, a relative change in temperature and a non-dimensional time, which includes all the relevant properties for this system. And you could get it through Buckingham Pi if you so wished. So this is an important solution. You can apply that if you want in a couple of ways to be able to look at the so-called Kelvin problem and Rutherford's solution to it. We did this already last time. We talked about our knowledge of the fact that we know what the geothermal gradient is. It's roughly 25 to 50 degrees centigrade per kilometer. We can define Fourier's law either as a heat flux over an area that we know, or just a heat flux per unit area, which is Fourier's law. And so if we know what the thermal conductivity is, and we know what the thermal gradient is, if we take these two parameters here, then we get the fact that the heat flow is something like, we did it last time, 20 or 50 milliwatts per meter squared. If you use higher conductivities, you'll get different values. And we saw that it varied between something like 20 and 150 milliwatts, depending where on the surface of the Earth we were. And it just turns out that the solar insolation, if you do the calculation, Arizona probably is something like 1,400 watts per square meter. So this is something like 10 to the power 6 different. So it's a very small thermal flux, but it's a very large body of material with a great amount of heat locked in it. The so-called Kelvin problem is that if you want to calculate the age of the Earth, what you could do is you could say that the crust which fits on top of the Earth has magma under it, and it exists at, I don't know, 1,000 degrees centigrade. Since we can stand on the surface of the Earth and our feet don't melt, we know that the surface of the Earth, is, as we probably said, is maybe about 10 degrees centigrade. Groundwater in central Pennsylvania is about 10 degrees centigrade, essentially 0 degrees centigrade. So in other words, at some stage, this whole thickness of the crust would be 1,000 degrees centigrade, and it's cooled from the surface, so now that it's cooled. And so if you think of applying a quenching temperature at the Earth's surface and seeing how long it takes for that thermal wave to penetrate down to the bottom of the crust, which is about 60 kilometers or so, you can use this expression here for 1 being equal to the time, dimensionless time it takes to get there. And since we know that this is maybe 60 kilometers, we know that this is 10 pi meters squared per year. It turns out that the time for that to happen is something like 120 times 10 to the 6 years. So that's 120 million years. But we know that the age of the Earth is something like 4.3 billion years. And so the discrepancy between this exists from Kelvin, smart guy. We named our reference temperatures after him, Lord Kelvin, professor at Glasgow University. Rutherford, professor at Cambridge from New Zealand, who discovered radioactivity with cloud chambers. The story goes was sitting in a meeting where he was going to announce his discovery of radioactivity, and his estimate for the age of the Earth to be not 120 million years, but 4,000 million years. And the difference is that if you allow for radioactive decay in the crust and below, that provides a source of heat that allows the temperature control within the subsurface to be much more longer lived than you predict if you're just looking at a dead planet that is purely conducting. In here, you're generating heat all the time that is coming from radioactive decay. And so that means that the time taken to cool is off by a factor of, I guess, 40, of the order of 40, right? Okay. So that's conduction in the crust. We said that conduction is a very inefficient way of getting heat out of a system. We'd much rather use convection. And the methods of convection that are important to geothermal reservoirs would be that in the subsurface, we want to create fractures, and we want to intersect those fractures with boreholes. And in those boreholes, we'd like to be able to pump in fluids which would go through the fracture network in some way and then come back to the surface. And we like it to be coming back to the surface hot rather than going in cold. And so to do that, the only way that we can do that is that the water goes in cold. The only way it's going to get in hot is if it picks up by conduction heat from the surrounding rock that the fracture goes through. So this boundary here has to be a conductive boundary which feeds water into the water which is passing it. And so it's like this. This would be the wall of the fracture, which would be along here. Heat goes in by conduction. This is the thermal conductivity of the rock. Again, we called it lambda before. And once it goes across this boundary into a fracture, so this is a fracture that has water flowing in it. So this is ostensibly cold water. The temperature at this boundary, if I can draw it, would look like this would be X. This would be temperature. Then physically what's happened is the water flows past this. The rock temperature is quite high, but because the water quenches it, it would change the temperature of this at the wall to basically to do this. So it's really not very different, and that's why we talked about it. It's not very different to this process here. Something heats this up or quenches it, and as a result of that, it saps heat from this. This gradient here is dt dx, which is what turns up in Fourier's law. And so the rate at which heat will travel by conduction out of the rock into the water which is around it is kind of the rate limiting process. It's by far the slowest process. If it turns out that this separation between fractures is tiny, you could think of it if the size of these rock blocks were grains of sand. Grain of sand would give up its heat very quickly because the characteristic length over which this would flow would be very small, and therefore the dimensionless time would adjust because this would be a very small number. And so a real time would end up being a very big dimensionless time, which would mean that it would be on this equilibration side, and it would equilibrate to infinity at a very early stage. Typically, we're not blessed with that, and so the whole problem of dealing with subsurface geological heat exchangers is that they're rate limited by conduction in the rock to the water, and then advection of the water out of the system. So this would be the density of the water, or the fluid that's in the system. So this is heat conductance of the rock, temperature gradient in the rock, and distance into the rock. This would be the density of the fluid, water typically. This would be the velocity of the fluid. This would be the specific heat capacity of the fluid, and this would be the temperature that's picked up in the fluid. And this would be the heat transfer that would come as water as the carrier fluid, heat exchange fluid, that would be brought up to the surface and then used in some way. So that's the whole essence of what we're attempting to do. And so that is our challenge. So at least now you understand that the non-dimensional parameter of heat transfer, which is equal to thermal diffusivity, time, and we want this to be very large, because we know at very large times we've essentially taken all the heat out of this system. So the heat within this system would be basically the area under this full curve. So volume of rock times a change in heat, specific heat capacity, and the density of this rock would be the amount of heat that would be generated. And to get that, we want to get to T infinity, where we've taken all the heat out of the system. So we only get to T infinity when this is very large, so we can do that when thermal diffusivity is large. Doesn't happen. We know it's 30 meters squared per year. That's not a very big number. Where we've done it for a long time, we don't want to wait for 1 million years to get it out. We want it in days, certainly less than 30 years. So the only way we can do that is to make the separation between fractures very small. The whole idea of hydrofracking shales make the separation between fractures small, so the diffusion of gas by Fick's law is fast because the distance it has to travel is small. Exactly the same it's exactly analogous in geothermal reservoirs. You want the spacing between adjacent fractures to be small, so you want the other fracture to be not very far away over here, because then you'd get the conduction of heat not only into this fracture that's flowing, but also into this fracture. And of course, the rate at which it does that is given by the gradient, which is controlling Fourier's law. So that's actually the essence of the holy grail of geothermal reservoirs, is to be able to get that heat transfer from the rock, which is the rate limiting step, and into the fluid. And the difficulty in doing that is actually the same, analogous to what's going on here, is that it's kind of like a wind chill effect. So wind chill effect is that we're cooled down by air going past us. So it takes the heat very efficiently from our skin, but the transfer of heat from our interior to our skin is controlled by exactly this process, by conduction in us, even though we're 90% fluids, probably, water. It's by conduction onto the skin. If the wind velocity is 0, then we're quite efficient in not taking heat away, because this boundary condition here will actually warm up. Of course, clothes insulate you and allow this boundary layer to warm up to the same temperature as the body or the rock underneath it. And as a result, there's no gradient in temperature here, and so there's very little heat transfer. And so the mechanism by which that occurs is governed by convection from the solid into the fluid that's going around it. This heat flux in the water is controlled by a so-called Nusselt number. Another dimensionless number, which controls the rate of heat flux across this boundary, a function of the hydraulic thermal conductivity, the difference between the temperatures in the medium, the wind or water, and the rock itself, the solid, and some kind of characteristic length over which this flows in this direction. And it's defined, again, in terms of two other parameters: Reynolds number, density, velocity, characteristic length, and a viscosity of the flowing fluid, and a Prandtl number, which is specific heat capacity, viscosity, and the thermal conductivity, which we call lambda. So those are the key components that we need to deal with. Josh, yeah.
What about is the scale of ideal spacing between fractures?
Smaller the better.
You have to worry about reservoir depletion?
If you had a reservoir which was made out of sand grains, you could just so if you had a reservoir that was made of sand grains, then what would happen would be that you would strip all so you go in here. So this is in and this is out. So what it would do is it would, I'm trying to think, so the temperature change along this system, if it was, starts off cold, this goes in, so the temperature change would be that it starts off, so the water starts off cold, and it comes out, by the time it comes out to the other side, it does this. So in this particular case, if it was a sand reservoir with tiny grains of sand, so you strip off all the heat, these would be successive temperatures in the reservoir as you take fluid out of here. So it would just deplete the reservoir backwards. You'd be completely depleting it as it moves back. If this is a system where you're flowing within a fracture, then what would happen is it would go in at 0 degrees here, or very cold, and it would come out of the reservoir at this slightly larger temperature because it's picked up no heat from this. So your temperature of your reservoir will only deplete once you've completely exhausted the, I guess we called it H last time, right? The heat in it would be equal to the volume of the reservoir times the density times the specific heat capacity times the temperature change between inlet fluid and outlet temperature. And so this is a very inefficient heat exchanger because it'll go in at a low temperature and it'll come out at a low temperature as well. So this will take a long time to deplete because that, which is, your reservoir lasts for a long time, but you get no power out of it. Here your reservoir will last as long as the heat is in there to supply it. It'll come out maximally hot all the time, but once enough fluid has gone through it, so the fluid, I guess, rho would be actually a mass rate, would be a mass rate, and then this would be a heat rate. So this, it would take as long as it would take to completely remove all the heat energy from this. So it would come out quickly, which you'd want, and it would only deplete once it's gone back to remove everything from its sweep, the flow path it swept. So the closest spacing, the better.
So usually they don't worry about depleting it too fast then, they try to maximize the output?
You want to, well, from this expression here, right, remember, you have each of these parameters. You have mass flow rate, specific heat capacity, and temperature change. So this is in watts. This heat rate, thermal power in watts. So you want to maximize this, and you want to maximize this. If either one of these is 0, then the heat rate's 0. So that's why in this case the heat rate is 0, because the temperature is coming out at is the same you're injecting it at. If this was really fine sand grains and you're getting the full temperature out of it, that the reservoir, but because it's sand grains and you can't push it through quickly because the permeability is too low, then that would deplete this parameter and this would be high. So that's bad too. So balance. Not many rock reservoirs where the spacing is too small. Yeah, it's usually the problem. So in EGS reservoirs, it might be a meter spacing, or it might be 10 meters spacing, and so you can calculate from this dimensionless time how long it takes to deplete a block to that size. And so even if you're infinitely efficient in terms of getting it out by convection, it's rate limited by how quickly you can get the heat out of that block. And you can do that calculation now. Radiation is not really relevant to us, but if you want to get the power that comes from a black body, the sun, or absorbed by the Earth, it's given by the emissivity, which is a number between 0 and 1, dimensionless. Stefan-Boltzmann coefficient, which has units of watts per meter squared per Kelvin to the -4, 1 over Kelvin to the power 4. And you can calculate that emissivity in terms of the temperature of something, and you can calculate what the absorption is, but based on that temperature. So it's the same equation. So if you look at two different bodies, you can calculate the relative power that's exchanged between them by using the temperatures of those bodies in Kelvin, not in centigrade. It has to be an absolute temperature. Perhaps doesn't matter so much to us, but you can do this interesting little calculation by using the power. You can calculate the power that comes from the sun if you know something about its characteristics. So we have a value for this. Maybe I'll switch colors. We have Stefan-Boltzmann coefficient. We have an emissivity uncertainty magnitude between 0 and 1. We have the temperature of the sun, which is 5,800 degrees Kelvin to the power 4. And we have the total area of the sun, which is given by its radius. This is in meters. Haven't laid out the calculation here, but if you do the calculation, you end up with, for this radius and this particular area of the sun, you end up with 4 times 10 to the 26 watts. If you look at that being impinged away from the sun, then you can calculate the amount of power that gets put on a 1 meter by 1 meter square. That's the distance of the Earth away from the sun. So if you take a 1 meter by 1 meter square at the Earth's distance, 1.5 times 10 to the 11 meters, it's about right. So it's 93 times 10 to the 6 miles, which must be about 150 times 10 to the 6 kilometers. Which is right, yeah. So that's kilometers to meters would be 10 to the 9, 1.5 times 10 to the 9. So that's exactly the distance to the Earth. And so if you take this power spread over an arc, which is equal to a 1 by 1 patch, so the angle given subtended for a 1 by 1 patch is the area of the patch divided by the area of this shell, which is 4 pi d squared. This is the distance to the Earth. So the shell that is at the radius of the sun from the Earth, 4 pi r squared. And that turns out to be a fraction which is small. And if you multiply the total power from the sun by that fraction of this angle subtended by the whole of the power, it ends up being the power from the sun multiplied by this angle area subtended. And it turns out to be what we know, this is Arizona. So this is 1.5 kilowatts per meter squared. And so this is the number we contrasted earlier with the fact that the power from the Earth is something like, was it 200 milliwatts? Or was it, 1,500 milliwatts is large, or 150 milliwatts was the largest, and the lowest magnitudes were of this. So it dwarfs it by comparison. Same deal. Yeah, won't go through the calculation you have in your notes. So if you take that area of 1 square meter on the Earth and look at the section, which is the whole cross-section it sees to incoming solar power, and multiply that 1 meter squared by the total area face on to the sun, it turns out that the solar insolation is 180 times 10 to the 6 gigawatts. We burn something like 10 to the 15 terawatts of fossil fuels. So this would be something like 180 times 10 to the 3 terawatts. So the amount of solar power we get over the whole surface of the Earth dwarfs this by 18,000 times, I guess, 18,000 times larger. And so you can do lots of other calculations, which I won't do, which are not relevant here. The other final parting shot before we get back to thermodynamics was we mentioned that the whole greenhouse gas problem when we talked about Sokolow and Pakala's stabilization wedges was that there are huge fluxes of carbon between different reservoirs in the solid Earth and the ocean and the atmosphere. And they may be tens of gigatons of carbon per year. But the only imbalance with that is that we supply something like 7 gigatons per year of carbon, which is from fossil fuels. 7 gigatons, maybe 10 gigatons, multiplied by 4 for CO2 instead of carbon, and you get 40 gigatons a year. It's just this small imbalance that causes the problem. And the problem is that we rely on CO2 in the atmosphere to keep in some of the insulation by reflecting back from the atmosphere the infrared radiation that's developed from the interaction with the surface. And if we didn't have that CO2 in the atmosphere, it would all be lost to space, like on the moon, and there would be no atmosphere, and there would be no 20 degrees centigrade or 10 degree average temperature on the face of the planet. So the greenhouse effect is important. We wouldn't be alive without it, but too much greenhouse is a problem, and it's relatively sensitive because it's caused by a feedback system in terms of all of the interacting processes on the Earth. So anyway, so to be able to make electricity, we need to have a phase change in fluids, not just sensible heat, which is what conduction and convection is, but talk about a phase change, which is non-sensible heat exchange. We need to use the first law of thermodynamics, which says that heat is neither created nor destroyed. It comes from, thermal energy is neither created or destroyed. It is supplied by heat defined within a system, work that is allowed to be done by that heat, and changes in internal energy, which results from that. We can think of that being defined as heat input into a system, work done by the system, and that resulting in a change in internal energy. So that's our system that we're dealing with. And we have to afford a sign convention which is attached to that. And to use any heat conversion system, the Carnot cycle is one mechanism by which we can do that, which relies on this particular behavior which is shown here. And so in our particular case, we would have geothermal fluids. And in a kind of regular thermal power plant system, we take water, liquid water, we heat it by supplying heat energy to it. That heat energy allows that to change phase from a liquid to a gas, and by doing that, it runs through a turbine. The important thing it does is it's changed from a liquid to a gas. It goes through a phase change, but it doesn't change a temperature. So it's a latent heat behavior, whereby there's a change in energy in the system which is run by latent heat, but the temperature doesn't change as it goes from the boiler to the turbine to the system. Once it comes out of the turbine, we use that to provide heat in the system, work in the system. We then take the hot fluids that come out of it, we condense them back from a gas, the vapor, into a liquid. We then take that vapor and liquid by compressing it, and then we pass it through the same cycle again. So that is kind of replicated in this particular cycle here. So as it goes from A to B, it's heated up by putting coal to heat this up. This is provided by our geothermal fluid. The heat input into the system is Q1. In going from Q1 to the turbine, it doesn't change temperature. The lower axis of this is specific volume. So specific volume is equal to 1 over density. It'd be density of the fluid. So specific volume is because density has units of mass per meters cubed, kilograms per meter cubed. So this is a volume, hence its volume. So an increasing specific volume is an increasing actual volume if it's constant mass. And so this is going from a liquid to a gas at constant temperature by flaring. This is the amount of work that is able to recover from the system as it's then cooled down and condensed. It's cooled down to this. It is pressurized by providing compression, which recovers heat from the system, and as a result it ends up back as a fluid. And at this stage here, since it's gone through a full cycle, the changes in internal energy within the system, delta U as we've defined it, have always at any point will come back from its initial value as it marches through the system. It'll always be the same at this point. So from A, we input work to get it to compressor by putting energy in the system. So this is the work that we put in here. We allow heat to provide energy by thermal energy in the system. We allow it to go through a boiler by providing Q1. Once it's gone through the boiler, we make it do work for us by the turbine. Once it's gone through the turbine, we condense it by recovering heat from it. We saw those units with the fans on it at Waraki by condensing ambient temperature through it. And as a result of that, we get liquid that we can then re-inject. And in our case, we just bring more geothermal fluid into the system, which is already hot, that can boil, etc. So from the first law, we know that the heat input to the system is heat input and heat recovery. The difference between those is the amount of heat into the system. Since the amount of heat into the system and out of the system has to equal, is defined by the work that's done. And so this net work output has to equal the amount of thermal energy, because the change in thermal energy in the system has to be zero. As we've made the point here, as it ends up back at the same point, it must be zero change in internal energy. So if it's zero change in internal energy, then this work must equal this heat exchange. So we can substitute the amount of work done by the system by this heat exchange here, Q1 minus Q2. The amount of heat that we've applied to the system is just Q1, and so we end up with this. So the efficiency of the system is how much work we've got out of the system for how much energy, heat energy put into the system, is just the ratio of these. If we convert these into temperatures, so this would be the temperature, this would be the ambient temperature external, and this is the ambient temperature internal, then this gives the efficiency. So if you have something that is operating at 100 degrees centigrade to boil, and you're cooling it back down to 0 degrees centigrade, then the relative temperatures in terms of absolute temperatures would be roughly 400 Kelvin and roughly 100 Kelvin. Sorry, 300 Kelvin. So 1 minus 300 over 400 is something like 20%, 25% efficiency. So that's defined by the efficiency of this system. If you work with supercritical fluid, which instead of being 100 centigrade is something like, critical point of water is 350 centigrade, so maybe it's 400 centigrade. That means that it's 700 Kelvin. And you're bringing it back down to 0 degrees centigrade. It won't be 0 degrees centigrade, but that would be 300. So the efficiency of this system would be 1 minus 3 over 7. So it's less than, more than the half. So, which is greater than, say it's about 60%. So the hotter your system, always, the more efficient it is in converting heat energy to work, just by virtue of this relative efficiency, which is defined in terms of the thermodynamic behavior. If we look at the quantities that define these systems, they're defined in terms of the temperature of the rock or the fluid, the pressure, specific volume, which we just defined as being a volume per unit mass, and also specific internal energy, enthalpy, and entropy. These are just values of internal energy per mass, so it's per density, per unit mass. And so we can define enthalpy as a function of internal energy plus pressure. You can also write this as pressure multiplied by 1, so this is specific volume, which is 1 over density. So this is pressure per unit mass, is another definition certainly that we used in 303. And if we look at behavior in terms of how enthalpy changes as a function of internal energy, if we work with a closed system, then we can, from the ideal gas law, we can say that the product of pressure and volume, specific volume, which is just the ratio of pressure to density, remains constant. So if we take the changes in these properties, which is what this is, then this doesn't change if it remains constant, and we're left with the change in enthalpy in the system being related to the change in internal energy. And so if we put that into the first law, then if we get heat put into the system but at constant pressure, then the change in enthalpy in the system has to be equal to that heat that's put into the system, which will be the total change in enthalpy, which is delta H. Likewise, if we keep it as no heat exchange, an insulated system, there's no energy that goes out of the system, all the heat is trapped in it, and then the amount of work that we do in the system will be equal to the change in enthalpy that we put into the system also, just with a different sign to it. We can define entropy as the third of these as change in disorder. It's specific entropy, so it's change in disorder per unit mass, and so that is a change in heat supplied to the system divided by the ambient system temperature, which is in Kelvin, degree Kelvin by definition. And so this allows us, if we use entropy, to be able to define the phase behavior of a fluid, which is what we're going to use to be able to get heat transferred within our system and to turn heat into mechanical work through a turbine. So we can look at how temperature, a phase diagram for water, changes as a function of temperature and entropy. And so we can look at these bounds as we increase the entropy of the system. We start on this side of a zone where it's liquid. It goes through a region where it's steam, water and steam as a mixture, and then on the other side it's purely vapor. We can define the behavior at the critical point. Critical point by definition is where water and steam coexist at the same pressure. And the temperature for this is something like 350 centigrade or 650 Kelvin, of that order. We can look at a path across this chart where we change from being 100% steam, 100% water on this curve, 100% steam on this curve, and at portions between that, it changes kind of linearly between those two components. If we go across a path which is isobaric at the constant pressure, then if, say, it's atmospheric, it will go from water, this would be 100 degrees centigrade, and this would also be 100 degrees centigrade on this side. It's going from 99.999 to 100.001 at this stage. It doesn't change pressure as it goes across here, and this is the phase change that makes the behavior change across it. And if we go at a higher pressure, then we can sustain larger temperatures in the water. So this is increasing temperatures. You go up here. If we depress the temperature, then this would also be an isobaric path across here, ultimately going up here, but this would be less than atmospheric. And so we can look at how these different properties would chart across these three regions of liquid, steam, and steam only by looking at the properties of the fluid as we go across that. And so if you take a packet of material within the system, within your reservoir, then it may be a mixture of fluid and gas. So if you go here, it would be 100% fluid and 0% gas, 100% gas, 0% fluid, and so it'd be 1 kilogram of liquid, 0 kilograms of vapor. 100%, 1 kilogram of vapor, 0 kilograms of gas. And so the total mass has to be those two components. If we take that as a kilogram, then these must always sum to a kilogram. If we take the total volume, then we can define the volume of the fluid and the volume of the gas as being the total volume. If we take this volume as being defined, so the definition of the volume, so density is equal to mass per volume. So this means that volume, total volume, is equal to mass over density. So volume of fluid has to be the mass of the fluid by the density of the fluid. That's all we've done here. And the volume of the gas has to be the mass of the gas divided by the density of the gas. And so this term here, 1 over rho gas, is this. This is a specific volume of the gas, which we defined for use in our, this was specific volume. And so if that's the case, then we can write our specific volume as the total volume divided by the mass. If we have this, we can do this. We can add those together. This total volume here we have as this. And so if we combine those and we register the fact that on this boundary here, we can define the mass of gas divided by the total gas. We said that this will be equal to 1 at this boundary here and equal to 0 here. So we can define this parameter x, which is just the ratio of the mass of gas, vapor, to the total mass. And by definition, 1 minus x will be equal to the mass of fluid divided by the total mass. And so we can rewrite this expression in terms of these substitute components. And so physically, I guess all it's saying is that as you go across this isobaric path, you start off at 100% x. So this is x, which by definition is the mass of gas per unit mass. So it's 100% of the mass is other way around, like, so this would be the mass of gas. So yeah, okay, so the mass of gas would be 0 at this point, and the mass of liquid would be 1 minus the mass of gas, which would be 1. So this would be equal to the mass of fluid. So one would be 100%, one would be 0%. That's my reminder to stop. And so as we go across these merely scale in terms of linearly as we go across here. So as you go, you change the specific volume from 100% of one here to the other. So if you go at any particular location, halfway is 50% gas and 50% liquid. 100% of the way, it's 100% gas and 0% liquid, and likewise. So they just map as you go across the system by this. And the reason we do these is it allows us to be able to define the response as we go across this system at different temperature. And we know that this temperature change is due to a phase change, not sensible heat change, but due to a phase change in the system. So we'll use this next time. I didn't want to go through those last two slides anyway, but it allows us to define exactly what happens within the phase change that we get for liquid water, which we're trying to drive. And this is what allows us to input heat into a system and to get work, mechanical work, out of a system by the expansion using the idea of latent heat as water flashes to steam. And we'll use that last time. Okay, great. Thank you.